Thank you. I first wanted to thank the organizers for this wonderful setup and stimulating meeting. And what I would like to tell you is about some studies that we have been doing related to using the quantum nature of light for spectroscopy. In basically, quantum light has been developed, and we heard a lot of applications of quantum light in this meeting. And the primary motivation for that is to do like information processing or quantum computing to manipulate the field in order to move some information. In spectroscopy, we use the field to study the material system, like molecules. And in spectroscopy, you usually use classical fields. So we would like to merge the quantum field with spectroscopy and to see what can you learn by using quantum field on complicated matter that is not possible to do with classical fields. And we have been working on this over the past few years, and these reviews of modern physics that just appeared summarizes much of the stuff that I'm going to talk about. And I also recommend this book where the formalism is has been developed. And again, before I start, I would like to mention that I have some postdoctoral openings at UC Irvine, and any of you is interested, please talk to me. So what is multidimensional spectroscopy? You excite the system by several pulses, and you vary delays, you vary phases, you vary frequencies, and then you get a multidimensional imprint of your system, let's say as a function of the different delays. And the key point is that you calculate a polarization, you expand it in terms of the fields. This is with classical fields, and this response function contains all the information that you have about the matter. So here, this is a 4-pulse situation, so you have 3 time delays. And the field enters as a product of amplitudes. And when you do spectroscopy with classical field, that's what you do. When the field is quantum, you can use exactly the same formula, but you replace this product of fields by the correlation function of that product. And the correlation function contains the information about the wave function of the field and all the quantum nature. So instead of having 4 amplitudes or 3 amplitudes, in this case, you will get a product of, you will get a corresponding correlation function. And then in order to calculate spectra, you take these signals as a function of, let's say, 3 time delays, you do a Fourier transform, and you plot it in the frequency domain. That's what people doing in NMR, and that's what people do in optics. So for example, if you have uncoupled systems, you can get only diagonal peaks. This is as a function of Fourier transform with respect to 2 time variables. And if they are coupled, you get cross peaks, and the cross peak give you information about the coupling. So this is in 1 minute multidimensional spectroscopy that was first developed in NMR, and then it applied to optics. Now, in terms of describing the system, we can either use the wave function or the density matrix, and both give, in principle, you can do it either way. And what happens is when you want to describe the response function, when we do it with the density matrix, we use such diagrams where this is the cat and this is the bra, and the arrows contain the interactions. And when you do it with the wave function, you write such a loop and you go forward and backward. The Keldysh loop has been mentioned here a few times. So this is equivalent to doing the Keldysh representation, where you go forward and backward in time, and you have artificial times. Now, if you do it like that, you have more terms when you do it like that, because here I keep track of the relative time ordering of the bra and the cat, and I have 2 to the n terms if I have n interactions, and here I have only n plus 1. So you have a many-body system where you want to work with the wave function with all the degrees of freedom, you use this. If you want to use a reduced description with density metrics, you use this. So both of these representations are useful. And then if you have such a diagram, you can translate it into an expression for the response function where you have couplings and you have the frequencies and so on, and then you have your microscopic description. So that's basically what we do in multidimensional spectroscopy, and this has been started in NMR, in the radio waves, and it's going up the frequency regime because you need a control over the phase, and the control over the phase becomes harder and harder as you go to higher frequencies. So right now, there are applications to the UV. I have been doing a lot of work on pushing it to the X-ray because there are some new X-ray pulses, and in principle, you can push it to the gamma ray and study nuclear states by pulses, and so on. And the time scale here is limited to femtosecond, and here it could be attoseconds, and here you need zeptoseconds, 10 to the minus 21. So these pulses exist, and such experiment will be done in the future. So what is the twist that I want to talk about is what happens if I use a quantum light. And what can I learn with the quantum light that I cannot get with classical light? So we consider the following model of quantum light. This process is called parametric down conversion, where you come up to a nonlinear crystal with the frequency of the pump, and then it breaks into 2 frequencies, omega 1 and omega 2, such that omega 1 plus omega 2 equal to omega p. So these are twin photons. They must be generated together, and they come within an entanglement time, which could be sub-femtoseconds. And then the wave function of these twin photons, it has some envelope, and then it's A dagger times the vacuum. So this is the pair of the photons that we are talking about. Now, as I mentioned, such entangled photons have been studied in quantum information, lithography, and communications, and our goal is to apply them to spectroscopy. So this is an example of a 2-photon absorption. The signal will be given by a correlation function of matter times a correlation function of the field. So if I have that model of the twin photons, I can calculate this correlation function and then see what happens. So just as a feeling, if I have this 4-point correlation function, for classical laser field, it is simply a product of amplitudes. For entangled photons, it can be factorized into the E dagger, and the EE into a product of 2 2-photon amplitudes. And if you have stochastic light, nothing quantum, you should factorize it in every possible ways. And in this case, it gives you this. So these are 3 realizations that will give you different spectroscopic signals. So it's like looking at the matter through different windows that are controlled by these correlation functions. Okay, and then you can do it also in the frequency domain, and you write these correlation functions in this way. So that's totally equivalent. Okay, so what do we have different with quantum light compared to classical light? The simplest experiment that I can do with this is 2-photon absorption. You come up with this pair. The molecule absorbs 2 photons and it goes into a doubly excited state. With classical light, this process scales like the intensity square of the light, because you need 2 photons, and so it gets like the intensity square of the light. If you want, you need the 2 photons to come in the same time, and the probability of that happening goes like the intensity square. However, if you use these twin photons created by the parametric down conversion, we find that the 2-photon absorption signal scales linearly with the pump rather than quadratically. So this is experimental results by the group of Ted Goodson on some organic molecules. You increase the intensity, so there is a region where it's linear, and then at higher intensity, it becomes quadratic. And the way to think about this is that the light, the photons comes in pairs, and each pair are twin photons that were created together, and they come within a few femtoseconds. And so when one photon is there, the other photon is there automatically. So in a way, the 2 photons act like a single particle. And this is why it is linear with the intensity. As you increase the intensity, you get more and more pairs of photons, and statistically, you will have the possibility of one photon coming from one pair and another photon coming from another pair. And then you lose the quantum effect, it becomes like classical light, and you get the quadratic behavior. So at weak intensities, it's linear, and then it crosses over to quadratic. And that's a very dramatic effect, which means that you can use nonlinear spectroscopy with much, much weaker signals, as much as 10 to the 10 reduction in power, and you can still get the signal. So this has been suggested as a way to use this for example, if you want to do imaging with nonlinear spectroscopy of biological samples and you don't want to destroy them, you can do the nonlinear spectroscopy with weak fields. So this is the simplest manifestation of quantum light, and it has been demonstrated experimentally by several different systems. Okay, so in this thing, you don't learn something new about the system. It's just that you are able to do the experiment with much weaker intensities. And of course, this thing will translate into other nonlinear techniques that will scale linearly with the, or a lower order with the field. Okay, so now let me show you another application which makes use of the unusual time and frequency relationships of these photon pairs. If you just have classical light, it's subjected to the Fourier limitation, which means the broader it is in frequency, the narrower it can be in time, and there is a delta omega delta t greater than 1. So time and frequency are conjugated, and you must lose frequency resolution if you want to have high spectral resolution. The entangled photons do not suffer from this because there are more degrees of freedom here, and the time and the frequency are not necessarily conjugated. And I want to show you a nice example where this can be used. So let's take a system where you can create this parametric down conversion. And since omega 1 plus omega 2 equal to omega p, I can have omega p to be narrowly distributed But then omega 1 and omega 2 themselves can be very, very broad. So each individual photon can have a broad distribution, but their sum is constrained by the incoming frequency. And such pulses have been created, for example, by the group of Wormsley. So we have here two time scales. This broad distribution determines the entanglement time, because the two photons will come within this time determined by this entanglement time, and this is the sigma is the time that is controlled by the pump. So this is the formula for this correlation function. You see that omega 1 plus omega 2 is controlled by sigma, but omega 1 minus omega 2 is controlled by T. So how can we use that? So, okay, this is just, first of all, another way to see it. This is the omega 1, omega 2 distribution. So omega 1 plus omega 2 is narrow, omega 1 minus omega 2 is broad. So let's calculate the following. Let's take an excitonic system where you have many two-level systems that they are coupled, and you get exciton states. So you have the ground state, you have a single exciton manifold. So if you have n two-level systems, you have n single exciton states, and you have n minus 1 over 2 exciton states, and so on. And let's say that we want to excite the double excitations and to study the two exciton states. So this is the probability of being, so I'm calling the states G, E, and F. G is the ground state, E is the single exciton manifold, and F is the double exciton. And I want to calculate the probability of going to F. And again, when you formulate it, you will need this correlation function, which we can calculate for the quantum light, or you can write it in the frequency domain. So we applied it to a relatively complicated system. This is called a reaction center. Don't be scared. This is an important ingredient in photosynthesis, where you have a collection of molecules called chlorophylls, and they absorb light, and then the light moves along the excitons, and it goes to some place called the reaction center, where charge separation occurs. So these systems have been studied a lot. This particular system has 6 chromophores, or 6 qubits if you want, and there are a lot of studies of the energy relaxation and transfer between them by using classical light. Now, here is the absorption spectrum of this system. The absorption is quite broad, and this is our level scheme, G, E, and F. I have in this model like 12 E's and like 40 F states. And if you look at the spectrum of omega 1 and omega 2 of the entangled light, it is very broad. So they cover basically this whole absorption spectrum. So now we calculate the probability to be in the final state. So we need 4 interactions, because we need 2 interactions on the cat and 2 interactions on the bra to bring me for GG to FF. And now, when you are in the single exciton manifold, there is a relaxation occurring, can be described by Limblad equation or a master equation, and so energies do relax. Okay, so what happens for this 2-photon double excitation when I do it with the entangled light? So this is an example of a pathway. I start with the ground state. I can excite to the 6 excited state, E6, and then this is based on the dipole moments and so on that I select these states, and then this can go to F23, to the 23's double excited state. But there is a relaxation pathway with 100 femtoseconds, where this relaxes to E5, and then I end up with F11. So this is the physics that can occur in this particular scheme. Now, what happens if you use classical light? When you go to this manifold here, you get relaxation, and the states get scrambled, and it's going to affect the distribution. So basically what happens is that when I use classical light, you get this relaxation occurring, and then you will basically get F11. You will not get F23 because of this relaxation. So you can say, let me make the pulse shorter and shorter, so the system will spend very short time in E6, and then I could beat this relaxation and I can go up. This is true, but then you lose the spectral resolution, because when you use a very short pulse, and then you cannot probe the F states with high spectral resolution. If you make the pulse longer, you increase the spectral resolution, but then you cannot compete with this relaxation. Now, what happens when you come with the entangled light? The photons come in pair, so when one photon comes, the other one is immediately coming and bring me up, which means it's a very short time and the process occurs instantaneously. But in the same time, I don't lose the spectral resolution because omega 1 plus omega 2 is narrow. And so I can probe the F states with high spectral resolution while at the same time eliminating the relaxation in the intermediate state. So this is an example of the population of F23 as a function of the entanglement time. If the entanglement time is long, the system is classical, which means the two photons are not so close, and then you get some population. But then when you decrease the entanglement time, you get enhancement of F23 because you are beating this relaxation and you get more into F23. For F11 is the opposite. If the entanglement time is long, you get F11, and then when you make it shorter, it will decrease. So the point is that we have both high temporal and spectral resolution because the time and the frequency here are not conjugated. The time is related to the difference in time of the two photons, and it can be very short, but at the same time, omega 1 plus omega 2 are narrowly distributed. So this is just another way to visualize this. This is as a function of the entanglement time, F11 as a function of the pump frequency. You see that you get an increase of the F11 with the larger entanglement time. Okay, now you can ask, nice, we show that we can get this resolution. The question is the quantum light, is the entanglement essential for this? Can we cook up a classical system or a classical light that will mimic this, and we don't need to use entanglement? As I said, in our approach, we were building upon this correlation function, and it was done with the entanglement. So one idea, you can think of using chirped pulse. A chirped pulse is a pulse whose frequency changes with time, either grows or decreases. And then let's say that I take two chirped pulses, one with a positive chirp and the other with a negative chirp, and I put them on top of each other. So what happens is, since omega 1 increases with time and omega 2 decreases with time, omega 1 plus omega 2 remains roughly the same. So I can have a situation in which, and this is purely classical, there is no entanglement here. So omega 1 plus omega 2 is narrow, while omega 1 and omega 2 themselves can be broad. So the question is, what will happen if you apply these classical pulses to the same system? Now, what I'm showing here is the probability to be in different F states, F11, F12, and so on, as a function of the pump frequency. And this is what I get with the entangled photons. So I get a good spectral resolution, which means I can distinguish quite nicely between the different F states. Now, if I use the chirped light, you can get something, but it's much less sharp. It's much less, the resolution is much less. And if you use stochastic light, you completely lose the frequency resolution, because with stochastic light, you have short, it's broad, so the frequency doesn't show anything. And so chirped light can be intermediate between the entangled and the stochastic. And the reason is, when you do the calculation, you have several pathways contributing to the signal, and the entangled photons select only those pathways, the desired pathway, that give me this effect. Whereas with the chirped light, you have background of other pathways that don't have this thing, like you interact twice with omega 1 or twice with omega 2 and so on. And so so you can mimic this effect with classical light, but the effect is much stronger when we use entangled photons. So this is the fluorescent spectrum, which is proportional to the doubly excited state as a function of the pump frequency. You see, with the entangled photons, you can resolve different F states, whereas when you use stochastic light or chirped, the F resolution is eroded. So, to summarize this, what I showed you, that you can use entangled light in order to achieve time and frequency resolution combination that is not possible with classical light. All right, now let me show you another application. And there is a group of studies now that are known as ghost imaging that use similar ideas for doing imaging. And we use it in order to study molecules by a Raman process. So, what is the idea? You take a system, you excite it to an excited state, and then you do a Raman process. You do a Raman process, and then you can study like vibrations. Now, in this particular experiment, the Raman process is done by a narrowband and a broadband pulse. The narrowband is picosecond, the broadband is femtosecond. And so what you do, the narrowband brings you up, and then the broadband stimulates you down, and then you look at the intensity as a function of the frequency, and then you will see resonances corresponding to the different Raman resonances. Now, here is a kind of joint spectral and temporal resolution. Because of the fact that you have the narrow band, you have a good frequency scale, and because of the fact that you have a broadband, you get a short time resolution. So this is within the classical boundaries, but this is why these experiments are done like this. So this is no quantum light. It is just a Raman experiment that shows you with a combination of a broadband and a narrowband pulse. All right. So now, let me show you what we are proposing. So this is just a summary of this. We take a system which has, it's a single qubit, but it has two states of the path that it can jump between them, which means the frequency of the system can jump between two different values. This is our model system. So you come with the excitation pulse, it's called the actinic pulse, and then you come with the two pulses, the narrowband and the broadband, and then you detect the broadband. This is how you do the experiment with the classical light. So now, how do we do it with quantum light? I take a parametric down conversion and I create a pair of photons, R and S. And what I do is, I take the photon R and I just bring it to a detector. And the photon S I use in order to generate the Raman process. So the photon S serves as the broadband in this Raman process, and the photon R is a reference. And what I do, I detect in coincidence these two detectors, okay? So I come with a pair of photons and I detect in coincidence. Now, what people do in ghost imaging, they don't do a Raman process, but they do a diffraction here, and then they scan this photon that did not interact with the matter, and then they learn something about this other photon because they are correlated. So you can scan a photon that did not interact with the matter and learn about matter. So I'm not doing imaging, I am doing a Raman process. So now, what can I find in these two detectors? Remember, I'm putting in two photons. I always get one photon here. Otherwise, I don't have an event. I am measuring a coincidence. So I always have one photon here. What can I measure here? So in this process, I can measure either 0 or 1 or 2 photons. These are the possible outcomes. And this is how it occurs diagrammatically. This diagram represents a process where I see 0 photon here and I see 1 photon in the reference. This is my excitation, and I absorb the S photon, and then I get 0 photon here. Here I emit the photon, and then I get 2, 1, which means I get 2 photons here and 1 photon here. And then I can absorb and emit, and then I get 1, 1. So these are the different outcomes. If I do the experiment with classical light, I just see the sum of all of this, and I cannot separate them. But by doing this coincident counting, I can separate these events and basically dissect the process into the different possibilities. So the idea is you do photon counting in coincidence, where one is a reference, the other does whatever you do. In ghost imaging, you use it to do imaging. Here we use it to do a Raman process, and then you can get the signal. Right. So when you formulate it, you need to calculate a certain correlation function of the field in order to get these different signals. So for the 0, 1, it turns out that you need a 4-point correlation function of the field. This is 2 S fields and 2 R fields. For the 2, 1 pathway, where you observe 2 photons, you need an 8-point correlation function of the field, whereas for 1, 1, you need 6-point correlation function of the field. So if we have a model of the entangled photon, we can calculate all these outcomes. Okay, so this is our model. We have the wave function. We do a Schmidt decomposition, and we can decompose it in order to see the degree of entanglement. The number of components is a measure of the entropy, or how many entangled states we have. And this is the spectrum that we obtain as a function of the Raman frequency. This is the absorption spectrum of the system. And then if I do the Raman with the classical light, I get this because I jump between these two states. And when I do it interferometrically, I get this. Now, here, the classical light is good enough so I don't get much new information. But if the jump between the states is fast, this is broadened. The resolution here is not good in the classical, but in the quantum case, you got a much better resolution. And on top of it, you can measure separately the different pathways. So the quantum light allows you, by the interferometric measurement, to basically dissect pathways and control the outcomes. Again, you can ask, can I mimic this by non-entangled light of some sort by classical correlations? The answer is that this is what the entangled give you. When you do classical light, you get much fuzzier results. So the entanglement is essential in order to obtain this degree of control. Okay. I think we have 5 more minutes. So what I will do, I will skip this one. Don't look. All right? Because I wanted to talk about the cavity. All right. So another type of quantum light is when you do experiments in a cavity. The cavity, you have the quantized electromagnetic field, and you have the polaritonic states. And we heard a lot of stuff about different experiments in cavities. So I would like to show you an experiment on a more complicated system. This is a system that undergoes, a molecular system that undergoes what is called conical intersections. Now, what is a conical intersection? You have, if you have a one-dimensional variation with some parameter, you get avoided crossing. But if you have more coordinates, the crossing is not avoided, and you can get conical intersections. And it turns out that many of the important photochemical processes in nature occur at conical intersections, because when the two states become close, they mix, you create a coherence, and it allows the transfer of population from one state to the other. So these are very important processes. And the question is, can you manipulate them by putting the molecule in a cavity? So this is more complicated than the models that we have been hearing here, because I have a molecule that undergoes a reaction. It's not simply atoms that undergo some vibrations. So as you know, the coupling to the cavity goes like 1 over the square root of the volume. And then if you have n molecules, there will be a square root of n on top of it. And then you can get cooperativity. Now, if the coupling is not too strong, you get what is called the Jaynes-Cummings model, where you get pairs of two-level systems that you can calculate separately, because the strength of the coupling is much smaller than the actual frequency. But when I do a conical intersection, the frequency goes to 0, and then it becomes an extremely strong coupling. You cannot use this Jaynes-Cummings model, and you have to solve the problem numerically in some other means. So this is the Jaynes-Cummings model. You have your two-level system, you have the cavity mode, and you have the coupling, and it gives you this. And many of the applications that we heard here about that. So what happens is the Hamiltonian is diagonal according to the number of photons, block diagonal, but there are these off-diagonal things between the blocks that can be neglected in the rotating wave approximation. But as I said, in this application, we cannot do it. So how can you solve the problem without the rotating wave? You can use a supercomputer and just diagonalize a very large matrix. What we did was we treated the field in coordinate space and we solved the Schrödinger equation in Q space. So we have two coordinates. One is the coordinate of the molecule and the other is the coordinate of the field. On numerical grid, we solved it so we don't do any expansion in Fock states. So it's basically an exact solution of this problem. So this is the model. You have this, it's sodium iodide. This is the ground state. This is the excited state. And here you have the avoided crossing. And this is how the non-adiabatic couplings looks. This is how the dipole looks. And this experiment was done not in a cavity by Ahmed Zawel. That was the first example of what is called femtochemistry. You excite, the molecule moves back and forth. Each time it goes through this, a certain fraction moves to the other potential. So you get this oscillation that decays, that shows you how the transition occurs. So now the question is, what happens if you put this molecule in a cavity? If you put it in a cavity, you need to add the photon field on top of it, and then you need to solve the dynamics of this coordinate with the field. So, as I said, since you cannot use the rotating wave, you get a complicated set of potentials. And the important thing is the following, that if there is no cavity, the population going to the other state grows in steps, like what Zawel showed. Each time I cross, certain fraction moves to the other pulse. Now I start increasing the intensity of the coupling, 0.05, 0.13, 0.19, and so on. And what you see is that when the coupling is strong, I can suppress the non-adiabatic, and after the process, I will come back to the same state. Because what happens is, you basically create a kind of bound state of the polaritons, and then it cannot go to the other state. So in a way, what you are doing here, you are manipulating chemistry by simply putting the molecule in a cavity. Now, there is one open question here that I have feelings about, but I don't have a full understanding of it, which is the following. The strength of the coupling is going like square root of n over v. N is the number of molecules and v is the volume, right? So the smaller the cavity, the bigger the coupling, and the stronger number of molecules, you have superradiance. Now, if you have atoms, this is fine, and this gives you superradiance. But when you have molecules, and each molecule is subjected to its own bath and fluctuates, this must erode the cooperativity. And the question is, will this n be replaced by some n effective? And will n effective go even to 1? We haven't done such calculations with a bath, and I cannot give an answer, but the point is, in order to have strong coupling to the cavity, you want to maintain the cooperativity. You want to maintain the square root of n over v, and the issue is whether in a complicated system n is reduced and you lose the cooperativity. So this is an interesting open issue that needs to be investigated further. Now, up to like 10 years ago, cavities were solely studied by physicists, and if you mention a molecule to a physicist, he gets scared. Right? You need to use atom and not to contaminate your system. But Ebesen in Strasbourg, like 10 years ago, had the, ambition. He put organic molecules in the cavity, and then he was able to get a couplings G of 0.7 eV, and we're able to see the polariton splitting. So he hasn't done chemistry, he hasn't done time resolve, but you can do molecules in a cavity, and then exploring this cooperativity should be an interesting future direction. Thank you.
Can I think of it as they're picking up some like coherent pathways rather than incoherent? And,
coherent in what sense? It's coherent in the sense that you are not sensitive to the relaxation in the intermediate state.
So you're effectively not populating that state.
Right.
So that it's a coherent excitation in that sense.
You stay there for a very short time. And so, but as I said, you can do it by doing a short pulse. So what's the big deal? The point is, if you do it with a short pulse, you lose the frequency resolution and you cannot resolve the F states. And here we can.
So I cannot just think of it as a coherent excitation. I mean,
yeah, you can think of the two photons like one particle, and almost simultaneously they go to the WX. Yeah, you can think about this like that. Yes.
Thanks.
Yes, I admit we have only studied this particular state of light. We haven't studied the other ones of quantum light. So this needs to be explored. Yeah, I cannot give you a general statement about any quantum light. Okay. It plays. You see, everything boils down to this 4-point correlation function of the field, and the entanglement basically entangles the different time variables. Instead of being E of T1, E of T2, E of T3, or T4, it becomes a more complicated function of these time variables. This is how technically it enters. And yeah, it will be nice to explore other types of quantum fields. Yes, absolutely. Okay, this is another scheme where the molecules interact. In all of these models, I assume that the molecules do not interact directly, and everything that I said is based on that. If there is an interaction, it becomes an excitonic system, okay? And there, of course, the exciton states could have this square root of n. There is no issue. But here I am talking about molecules that they only interact via the exchange of photons from the cavity, right? Aggregates is another story. It's another parameter regime.
Maybe it's more of a comment, but I think your last question about the what becomes the cooperativity in the presence of inhomogeneous broadening.
Right.
There's quite a number of work on that. I think you can generalize the cooperativity. I mean, maybe we can discuss afterwards, but there are some.
Sure, but is it maintained?
Well, it depends. It's the cooperativity is the ratio of the number of molecules times g squared divided by the inhomogeneous broadening and the cavity line width. And if this is bigger than 1, yes.
Okay. Inhomogeneous broadening is, I agree, it's something that is relatively easier to put in. What I'm talking here, that there is a chemistry, so every molecule, there is a coordinate that is breaking, and you cannot make all the molecules to break together in unison. There will be some, they will not be in phase, so that's a more complicated. But I agree, inhomogeneous broadening is easier to handle, yes.
Let's thank Shaul one more time and continue to the next speaker.